Then let's start today's lecture. The title is Application of Vibrational Spectroscopy from Hyper-Raman curves in Studies of Biomolecules. Yesterday, we ran some examples about the studies on small molecules. Right? Then today, we change the focus to biomolecules. What is the difference? Molecular. Okay. So first, we should recall our memory. When the light meets the material, there are three optical processes take place: absorption, emission, scattering. Okay? In this process, the energy of light is converted to the energy of molecule or electronic energy. Then this photon disappears. This is absorption process. In the emission process, a high energy molecule emits the light, and this molecule they activate to return to most stable electronic state. This is the emission. And when we irradiate the light, then sometimes such a process occurs and the direction of the light changes. This is Rayleigh scattering. When the wavelength changes, then this is Raman scattering. We know there occurs a scattering. Then we have learned how to utilize scattering for the molecular structure analysis. And this, you may remember this figure. So this is the intensity pattern of the Raman scattering is intrinsic to each compound. So this is so-called molecular fingerprint. As far as considering about the small molecules, it's very clear. Discussion is clear. It's because the small molecules exhibit a limited number of the Raman bands. There is a number of vibrational mode. Normal mode is 3 n minus 6. N is the number of atoms in one molecule. So as far as n is small enough, the number of the Raman lines are limited or less than 20 or something. So 20 or 30. As you see, this is the protein. How many atoms is there? You know, I have no idea. Probably this is more than 10,000 or so. If we consider this molecule and try to analyze the normal mode as in a similar way with that for benzene or ethanol or water, it's impossible because the nature protein changes its structure in the aqueous solution. That is the nature. Also, there are too many atoms, so the number of normal modes are huge. So it's not realistic to consider to analyze this molecule in the same way with the small molecules. So, in order to apply the vibrational spectroscopy, use huge molecules and biomolecules such as protein, we need to consider another different approach. And typically, the convenient way is to separate the protein structure into two parts, main chain and side chains. Okay, you know the protein is a polymer that consists of the unit of the amino acid. Then NH2CHRCOOH is the amino acid, and COOH and NH2 combines, and H2O is removed. Then here the peptide bond CONH is formed. By repeating this it becomes a long chain polymer. Blue part is repetitive NCCO, 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 right? So this is repeating unit, so we call it main chain. On the other hand, the side chain of the amino acid is various. So in nature 20 kinds of amino acids are known. And R1 R2, R3. So there are 20 possibilities. There are 20 possibilities. 20 possibilities. Okay? So there is a combination, large number of combinations of R1, R2, R3, R4. And anyway, this is side chain, and side chain of amino and order of the R1, R2, R3, R4, R5, R6 side chain determines the property of the protein. So the green part is side chain. So main chain determines the structure of protein. So, for example, this may be regarded as a bone, and this part is deeply related to the character of the protein, so it may be regarded as a muscle. Okay. So usually when we study the proteins, we separate the protein into two parts, main chain part and side chain part, and separately discuss what is the structure of main chain, what is the character of the side chain. It's a typical way. I don't know what it is. This is the main chain structure. NHCO, NHCO. This is the repeating chain, and this is main chain. And this part is so-called peptide bond. NCO double bond, NH single bond, CN single bond, NH single bond. It consists of 3 bonds. And this part has a resonance structure, O minus C single bond, CN double bond, N plus, and NH. Okay, for this reason, this part has a CN single bond has the character of the double bond to some extent. For this reason, OCNH is in same plane. Okay, this is O, C, N, H, and including the carbon in this part, and including carbon this part, it forms a planar structure. But this is one of the typical characters of the peptide main chain, or in particular the peptide bond. This planar structure is due to the resonance structure, where the CN single bond becomes the double bond to some extent. sometimes this O, C, and H is rotated to form O, C, and H. Okay. So this is the transposition. O, C, and H is the transposition. So this is called transpeptide bond. This is the cis position. Cis means the same side. O, C, and H is allocated at O and H are allocated at the same side of the NCN bond. So this is cis peptide bond. And in many cases, the peptide bond exists in the trans-peptide bond. And this rotation angle is specified by the angle omega. Okay. And in today's talk, we discuss n-chain structure, and so I should introduce a few parameters to specify the n-chain structure. One important parameter is the dihedral angle, phi psi. Okay, this is the rotational angle of this axis and this axis around this bond. Initially, A, B, C, D is, please regard A, B, C, D in the same plane. Then it's possible that CD can rotate. Okay, CD can rotate. And this rotation angle is called the dihedral angle. The definition is that when we watch this bond ABCD along with BC from AB side, CD moves clockwise, then it's positive. Counterclockwise, it's negative. So there are, please consider, there are two planes ABC and BCD. ABC, here is a plane. BCD, there is a plane. And fix a front, in this case ABC. And evaluate the rotation of the back, BCD. If it's clockwise, gives a positive number, positive degree, positive angle. If that is counterclockwise, anti-clockwise, please gives a negative sign. This is the general description of the dihedral angle. And in the case of peptide main chain, we use two dihedral angles to indicate what is the structure. Okay, this is NCCO, NCCO, NCCO. So this is main chain, right? This is the main chain. And as already I explained, the peptide bond OCNH and adjacent carbon forms a planar structure. It's also the case for the other side. There is one more planar structure, including peptide bond OCNH. And already I explained, this is a polymer that consists of the amino acid. Originally, amino acid is this part. So NH2 is covalently bound to COOH. So this bond is newly formed. COOH is bound to NH2, so this is newly formed. So this is one amino acid unit. Then we know this is R, alkyl side chain. And alkyl side chain is bound to carbon. This carbon is called C alpha. Okay? And from this consideration, we can set two planes that flanks C alpha. So let's consider this is the nth amino acid, then this is nth carbon alpha. Then for this carbon alpha, two planes we can define. Then please watch on this carbon. So you are here. Then let's see carbon. This direction is N side. This side is carbon side, C side. When we watch from this carbon alpha, N side, C side. So when we watch from this carbon, we can define the rotation angle or dihedral angle of this plane rotating. Then please use the parameter phi as a dihedral angle for the N side. Also, please stand on this carbon. Let's see the carbon side. Then this plane rotates. Okay? Then we can define the dihedral angle for this plane. It's rotating. Then we can use the parameter psi for carbon side. So for each nth carbon alpha, we can define two dihedral angles psi phi. And again, protein is a polymer that consists of amino acid. So there are carbon alpha, carbon alpha, carbon alpha, carbon alpha. This is carbon alpha, carbon alpha. So for each carbon alpha, we can define plane can define the plane. So about this carbon alpha, we can calculate 5 psi. About this carbon alpha, we can define 5 psi. About this carbon alpha, we can define 5 psi. So by specifying the dihedral angle, we can uniquely describe what is the extending direction of the peptide main chain. Okay. It's convenient. This is possible because we are sure this is a plane. So only specifying the rotation angle, we can exactly describe what is the extending direction of the peptide main chain. And sometimes peptide main chain forms a helical structure. This is alpha helix. Sometimes the peptide main chain stacking sheet structure. This is beta sheet. I might forget to introduce the definition of the direction of the peptide main chain. So this is the polymer of the amino acid, and this is the polymer of the peptide main chain, and N terminal is here, and C is connected to N. C is connected to N. C is connected to N. So starting from N and ending from with C. So we call it N terminal. This is the C terminal, carbon terminal, nitrogen terminal. And there is a consensus. Let's give the number, serial number about the amino acid from the N terminal. This is the first one, second one, third one, fourth one, and nth one. Okay? So this is unique number, not opposite. So the serial number is given from N terminal to C terminal, nitrogen terminal to carbon terminal. This is a good picture. So sometimes peptide chain forms an alpha helix structure. So this is N terminal, and helical structure is formed. This is C terminal. Sometimes it forms a beta sheet structure, so by extending form stacks with each other to form a sheet. Sometimes direction of the peptide main chain turns to this form the turn structure. There are various turn structure, beta 1, beta 2, beta 6a, beta 1 prime, beta 2 prime 1. So the difference is the position of the hydrogen bonding and the number of amino acid in this turn structure. And there are various turn structures. Also, there is a polychlorine 2 structure. So in this case, this state conformation is found from polychlorine, and in this case, CO bond directs perpendicular to extending direction of the main chain. And about the beta sheet structure, N, C, then turn go from N dash to C dash, turn N2 dash to C2 dash, turn. So by including turn structure, it may form such a sheet structure. This is so-called anti-parallel. Beta sheet structure. This is anti-parallel, right? Direction from N to C is opposite. N to C, N to C, N to C, N to C. This is so-called anti-parallel structure. And it's rare, but sometimes N to C, N to C, N to C. This kind of beta sheet structure is also possible. This is so-called parallel beta. Because it's parallel. Okay? There are two kinds of beta sheet structures. And it's very clear when we see the figures of this helical structure, its sheet structure. But this is our understanding, and it should be described in terms of the number. To describe these conformations, we can use dihedral angle. So in the case of alpha helix structure, phi and psi is nearly these values. If the dihedral angle or rotational angle of the peptide plane is fixed to these angles, and main chain is accumulated, then it is alpha helix structure. And in the case of parallel beta structure, alpha helix is something like this. And parallel beta NC, NC, all the same direction. Then the dihedral angle should be in this region. Anti-parallel beta value is in this region. Polychlorine 2. CO stretching directly perpendicular to the extension axis. Dihedral angle is something like this. So we know at a glance structure is different, but this is not convenient to deliver the information to someone else. So it's convenient to describe the structure by using the dihedral angle. So this parameter is employed in today's talk. So at least please understand why we introduce the parameters, so-called dihedral here. The purpose is to describe the main chain structure and convenient parameter. Then let's see the Raman spectrum of proteins. So there are many reports of the Raman spectrum of the proteins. You can purchase the protein from the market, sigma or whichever somewhere. Then I don't remember, or albumin, collagen, or I don't remember what is the abbreviation, but there are many proteins, and they are classified to some subgroups. This group is alpha helix rich protein. So the structure mainly consists of alpha helix. Then the appearance is something like this. The other second group is beta sheet rich protein. This is not correct, but please understand this is the beta sheet, not the helix. So there is a group of the proteins that contains large amount of beta sheet. And there is a mixture of alpha plus beta. Alpha and beta are segregated, for alpha and beta are intertwined. This is the third group. So typically alpha helix and beta sheet are a stable structure, so they prefer alpha or beta structures. And you see, regardless of the name of the protein, the appearance is surprisingly similar to each other. Okay? Here is amide 1. Here is phenylalanine. I explain what is amide 1 later. Okay, amide 1. Phenylalanine. So, information we can obtain from the Raman spectrum is similar irrespective of the proteins. Okay? So, this one-dimensional data contains the vibration of all the normal modes of the protein. And this is many bands are overlapped in the limited region. And it's impossible to separate this data into 10,000 of normal modes. So we should analyze as it is. So there is some established method how to analyze the protein structure from the Raman data. There are several peaks related to main chain structure, indicated by blue. And there are several there are several bands that is related to the main chain structure and side chain structures. So I start from some useful bands for the analysis of the main chain. There are amide 1 and amide 3. Amide 1 is here. This is the CO double bond stretching. O, C, N, H. And mainly it comes from CO double bond stretching. And it appears between 1600 and 1700. Amide 3 is the main chain vibrational. And it is mainly NH bending plus CN stretching. There are the different mode and peak position is different, but anyway, it is the vibration of main chain. So by analyzing these modes, we can get the information about the peptide energy. Okay. And second point is also a band that is related to base peptide main chain. So low frequency mode that is below 200 wave number. So this region also gives information of the main chain. So analysis of the main chain is possible by focusing on these peaks. First is an example of the amide 1 analysis. So amide 1 band that appears in the non-resonance Raman spectrum is useful for the peptide secondary structure analysis. So there is an established idea that alpha helix gives the amide 1 band CO double bond stretching band at 1655 wave number or in this region. So around this region, alpha. Beta 6 gives the peak at 1670 or higher region. So in this region, in this here, higher is here. This region, beta. And the random structure is in between. So by checking the peak position of the amide 1 band, we see what is the predominant secondary structure. Okay, so amide 1 peak is useful to determine the secondary structure. This is one key band to analyze the protein structure, in particular peptide main chain structure. Amide 3, I explained that is NH bending plus CN stretching mode. And this peak position is studied in the resonance Raman spectroscopy, and it is considered that the frequency is a function of the phi and psi and hydrogen bonding between peptide and water and the temperature. By detailed analysis, they derived some quantitative relationship between amide 1 peak position and the dihedral angle psi. Psi is the dihedral angle at the C-terminal site. So by checking peak position of the amide 3 band around 1200 or somewhere around here, we can estimate what is the dihedral angle of each protein. Okay. One more information obtained from the Raman spectroscopy is from low frequency mode. When we measure Raman scattering, we irradiate, here is a sample cell, we irradiate the laser beam to the sample and scatter the light occurs. Then we collect scattered light by lens and collimate and focus on and introduce the monochrometer. And if we do in the experiment like this, then the excitation laser beam or Rayleigh line is the strongest. So we put some filter to cut Rayleigh line. When we choose a special Rayleigh cut filter, notch filter, such as volume Bragg grating or I2 filter or some filters, then we can cut only the excitation beam. Here is an example. When we purchase cheap filter, Rayleigh cut filter, centered at 785 nanometer, then cheap filter cuts from 765 to 805. Okay, not sharp. When we purchase nice filter, so-called volume Bragg grating, then only 785 nanometer is cut. So width is very narrow. Okay, plus minus 0.25 nanometer. This is convenient to focus on the region near Rayleigh line. Usually we use such a filter, not the expensive one, and this is transmittance. By using this filter, we can cut Rayleigh line and find some gamma bands. But as far as using this filter, we cannot check this region. By using this nice filter, transmittance is something like this. So Rayleigh line is cut and we can detect some peaks near zero wave number. By doing so, we can detect some important bands at low frequency region. Okay, so using some nice filter is one method to detect low frequency mode. Well, there is one more method to detect low frequency mode. We can use a triple polychrometer. So this is the monochrometer. When we introduce the light, then this grating separates the light according to the wavelength. So different wavelengths propagate at different positions. And in order to cut the Rayleigh line, usually you put filter at this position. But we can use monochrometer in this way. Let's put monochrometer, 3 monochrometer together. Then put the slit here. Then dispersion of different color becomes larger and larger, and Rayleigh line can be cut very effectively. So we can detect low frequency region, also using triple polychrometer. And this is an example of the alpha chymotrypsin scene and lyophilized powder or acrylated or just film or denatured or SDS denatured, depending on the condition. Low frequency mode, this is a 0 wave number, this is 150 wave numbers. And so we can detect some structural change depending on the experimental condition. This is chymotrypsin and in principle data-rich structure. Okay, so by analyzing detail, we can get some structural change, information of the structural change. But in many cases, the low frequency mode has a broad bandwidth, and we compare a huge molecule gives single peak or unclear shoulder. So it may not be very easy to analyze low frequency mode. But anyway, this is a method to analyze the main chain structure. Then again, this is a Raman spectra of various proteins, and next let's discuss how to get the information of the side chain. Okay. From the Raman spectrum, we can mainly get the information of the tryptophan and histidine. They are aromatic side chains, and aromatic side chain has absorption. So it's possible to choose the excitation wavelengths to resonate to the absorption of these bands. So tryptophan and histidine can be selectively detected by resonance band. One more peak is cysteine. Cysteine gives a peak at 500 wave number, and when it forms SS bond. Or SH bond gives a peak at 2500 wave number. And in this region, there is no competing band, so it's easy, relatively easier to detect band of cysteine. So sometimes Raman spectroscopy is used to discuss the cysteine side chain structure. Okay, this is the protein structure, and it consists of many atoms. And we can separate it into main chain and side chain. And here is the absorption, UV visible absorption spectrum of tryptophan, histidine, tyrosine, phenylalanine. And we see tryptophan gives a large absorption at around 280 and near 230. By tuning the excitation wavelength to 229 nanometer, we can selectively excite the Raman process of this chromophore, that is tryptophan. Histidine is green, tyrosine blue, phenylalanine orange. We can selectively get the information of these aromatic side chains. That is, even though the protein is huge, we can regard this molecule as a group of the tryptophan, histidine, tyrosine, phenylalanine linked to the peptide main chain. And by choosing the excitation wavelength to 229, we can get the information of tryptophan, high histidine, tyrosine, phenylalanine in this huge molecule. Okay, it's very convenient. So this is due to the resonance effect. By choosing excitation wavelength that matches with the real excited state, intermediate state, we can enhance the Raman signal of the chromophore. Okay. This is a tryptophan side chain. And tryptophan side chain has a UV visible absorption. And in this region, there are two peaks, LA and LB. The transition moment directs this direction and this direction. And there is BB transition. And LA transition moment is sensitive to the condition of the NH hydrogen bonding. So the Raman band that resonates to LA mode is sensitive to the environment. Okay, this is the principle why some peaks are sensitive to the environment or structural change. So, sensitivity to the environmental structure is related to character of the excited state transition moment. So here is a typical resonance Raman spectrum of tryptophan. And it is known that 2, 3, 7, 16 are related to hydrophobicity change or sensitive to the change in the environment, hydrophobicity. It's because these peaks are related to certain excited states. And absorption intensity is affected by the environment. So the resonance, there is a solvent dependence of the absorption. So depending on the environment or change, difference in the solvent, absorption intensity changes. Then it results in the change in the resonance condition. Then change in the resonance condition results in change in the Raman scattering intensity. So the Raman intensity serves as a marker of the environment. Okay. So by this experiment, it is concluded that when the tryptophan side chain is in the hydrophobic environment and the donor of the hydrogen bonding, then W3760 becomes large, W2 becomes small. Okay, there are many conditions, but under the if the side chain satisfies these conditions, then we can interpret Raman intensity by considering hydrophobicity change. But this is one method to use your Raman spectroscopy in the protein structure analysis or protein environment analysis. So W3 is related to dihedral angle discharge of the tryptophan side chain. W7 is the doublet band, and doublet intensity ratio changes depending on the hydrophobicity. Also, W17 peak position changes in proportion to the wave number of the NH stretching, in other words, depending on the hydrogen bonding strength. So there are many studies to correlate intensity or peak position of the Raman spectrum with the environment change or structural change or hydrogen bonding change. So by establishing this kind of marker band, we can utilize the Raman spectroscopy to use the structural analysis. So this is important work, fundamental work. So someone must do, but many people want to use. Okay, so but this is important trial to establish the marker band. About the tyrosine, we can choose excitation wavelength to get the selective information of the tyrosine side chain. Always it is similar to the resonance condition to the tryptophan. So usually we get the information of tyrosine at the same time with the tryptophan measurement. But a few bands are available as an environmental analysis of the tyrosine side chain. One important feature is intensity ratio of this doublet. Okay. So depending on the status of the OH bond, if it serves as the donor of the hydrogen or donor acceptor of the hydrogen bond or acceptor of the hydrogen bond, intensity ratio changes. This is a typical intensity ratio. Lower side is stronger or higher side is stronger. It depends on the status of the hydrogen bonding of the tyrosine side chain. Also, the peak at so-called Y7A prime CO single bond stretch. The peak position changes depending on the hydrogen bonding. So if it is isolated and there is no hydrogen bonding, it is 1255. If it is hydrogen bonding donor, it moves to higher position. If this is acceptor, it goes to the lower position. Okay? So these two are widely used marker bands also to analyze the environment of tyrosine side chain. So sometimes tryptophan or tyrosine is allocated at the center of the ligand binding site, and when the ligand binds to the proteins, the environment of tyrosine or tryptophan changes largely, hydrophobicity changes. So initially it is exposed to water, but when the ligand comes, it becomes hydrophobic. Then we can analyze what is the structural change, how to accept ligand with tyrosine plane, tryptophan plane. So this kind of information is very useful to discuss what happens upon the ligand binding. Also here is an example of the histidine side chain. Okay. Histidine, this table is good. So histidine vibrational motion and vibration frequency changes depending on the metal binding. So there are two nitrogens, tau and pi, and depending on the binding of metal to the pi nitrogen or tau nitrogen or both, peak position changes. So the peak position of the histidine side chain is available to discuss the metal coordination. But the problem is that histidine symmetry is not very high, so the histidine band gives only weak Raman band, so careful measurement is necessary. Only one exception is to measure in D2O. In this case, the coupling between the NCN bending and NH stretching decoupled, disappears decoupled. Then large peak of NCN stretching and CC double bond stretching appears. So this is also useful and detectable peaks of the histidine side chain. So practically, these two peaks are used for the structural analysis of histidine side chain. If you can detect this table, is very useful. Finally, this is an example of the cysteine side chain analysis. Cysteine has a side chain of the SH group, and sometimes it forms SS bond. Or sometimes SH deprotonates. So this is an example of detection of the deprotonation arm with a peak change. Here is an amide 1 band that is a CO double bond stretching, and it can be available as a markup band to normalize the intensity. And at neutral pH, SH bond has an intensity, but gradually decreases. Okay, at pH 10, there is no peak. So we can plot the SH intensity with respect to pH value, and by fitting data point with sigmoid function, and we can determine pKa of the system side chain. So this is a good marker to analyze the status of the SH side chain. When SH forms the SS bridge, it gives a peak of the SS stretch near 500 wavelength. Depending on the conformation of the CCSSCC, peak position is different. So I skip the details of this table, but SS bond near 500 to 540 wave number is very characteristic, and there is no other peak in this region in principle. So in the case of protein structure analysis, so if you are interested in status of the cysteine side chain, one checkpoint is SH band, SH stretching. Another checkpoint is SS stretching band. Okay, and by taking peak position of the SS bond, you will see what is conformation of SS bond. I explained protein is a huge molecule, so it's convenient to separate it into the main chain and side chain. And this is not all. Sometimes the protein contains cofactors such as heme or retinal or some additional compound. And in many cases, this cofactor is very important for the protein to express its function. So it's worth considering how to get the information of the cofactor. In this case, Resonance-Raman spectroscopies are there. Heme, flavin, retinal. They have absorption in the UV or visible region. So we can tune the excitation wavelengths to achieve resonance enhancement. Okay? So they are well-studied cofactors. So I introduce one example about hemoglobin. So hemoglobin structure is here, and it consists of 4 subunits, so-called alpha 1, beta 1, alpha 2, beta 2. And each subunit contains heme. So there are 4 heme rings. According to X-ray crystallography, they say, sorry, I should explain what it is. Oxyhemoglobin, deoxyhemoglobin. Okay, so depending on the oxidation state of iron at the center of heme, it can be classified to oxyhemoglobin and deoxyhemoglobin, and its function affinity to oxygen is different. And X-ray crystallography is a powerful method to determine the X, Y, Z coordinate of each atom. So if they can prepare a crystal and apply to X-ray crystallography, it's possible to determine geometrical structure of the protein. Okay. Then based on X-ray crystallography, in the oxyhemoglobin, reduced state, R state, distance between iron and its ligand, histidine. Histidine may be too small. Here is a heme plane, and histidine is ligated from the sides. From the other side, oxygen comes, and oxygen attaches onto the hemoglobin, and hemoglobin carries the oxygen to our body. So the relationship between him and histidine is important. Then, according to the X-ray crystallography, they say the distance between iron and histidine is 2.07 angstrom in alpha subunit, 2.06 angstrom in beta subunit. In the deoxyhemoglobin, 2.20 or 2.21 angstrom in alpha, 2.16, 2.19 in beta. Okay. Do you know what is the resolution of the X-ray crystallography? In principle, error should be the order of 0.1, or a few years ago I checked it was 0.3 or 0.4. So even though they insist 0.7 or 0.6, but at least error is, this number is not exact, but at least error is large enough to distinguish the two states. The difference is within the error or the measure error. Average value is different, but error is still large, so they cannot distinguish. Here, we can apply a Raman spectroscopy. So when we focus on iron histidine vibration, frequency 220 or around here. In the case of deoxyhemoglobin, peak position is clearly different from these numbers. Even though the distance is considered to be less than 0.2 angstrom, vibration frequency sharply detects structural change. Okay, the advantage of the Raman spectroscopy shows up here. So even if the structural difference is quite small, it can be detected. Okay, that is the advantage of Raman spectroscopy. So depending on different oxidation state of the heme protein, peak positioning and appearance is different. So this is informative to analyze the status of the protein. Okay, this is the last slide. So they measured 35 nanometer excited laser Raman spectrum, and they selectively detected the signal of the tryptophan, tyrosine, tryptophan, tryptophan. Okay? Then they compare the deoxy state and CO bound state. The bottom is the spectral difference, and we see some positive peaks, negative peaks, or peak shift. In the protein structure analysis, it's possible to remove arbitrary residue by mutation technique. So we can eliminate one tryptophan and check this difference. If removal of one tryptophan does not affect this difference spectrum, then that tryptophan that is not involved in this event. If removing one tryptophan and some peak disappears, then we can assign this peak to particular tryptophan residue. So by repeating that kind of experiment, they could identify which residue is related to this spectral change. Then, according to their explanation, O2 binding onto heme beta oxygen comes. Then Fe histidine bond leaves and beta F helix moves. This helix is bound to heme by histidine ion interaction. But once this is cut, it moves a little bit. Then this movement breaks varying tyrosine hydrogen bonding. And aspartic acid tryptophan hydrogen bonding. Tyrosine 42, aspartic acid 99, hydrogen bonding. So rearrangement of the helix cut hydrogen bonding around here. Then the hydrogen bond is newly forms between 1 or 2 asparagine and 94 asparagine tryptophan 37. So this hydrogen bonding cut, then this hydrogen bonding is newly formed. Then this hydrogen drives the helix of alpha subunit to this direction. So attachment of O2 onto beta subunit affects the status of heme or in the alpha subunit, and it causes the allosteric effect. Allosteric effect means one attachment of one oxygen affects another binding site and facilitates the binding of oxygen. Or so synergy effect between two distant ligation site. So by this analyzing this different spectrum, they could explain what is the molecular mechanism of allosteric effect. Okay? So this is a very representative achievement of Raman spectroscopy and its application to the protein structure analysis. So by combining with a mutation technique, we can say which residue plays what role, and in particular aromatic side chains. Analysis of aromatic side chains becomes possible. Okay. Okay, so I prepared one more story, but probably it takes time, so it's better to finish at this page. Okay? Then this is all for the lecture.
we have some time if you want to discuss.
Okay, so today's talk is, you may think today's talk is some fragmented information knowledge, but when methodology is the same, when you want to analyze this molecule or biomolecule, please recall your memory, or resonance Raman effect is useful, mutation is useful, and some marker band is useful to get information about this feature, this feature, this feature. I want to know this part is there in literature. Then someone should study what is the relationship between structure and peak position or intensity or band width. So, you know, there are many bands in the Raman spectrum, and some band should be useful for your purpose. So today, anyway, I cannot cover all the examples about all the molecules in the limited time or in the lifetime. But so depending on your sample and your purpose, please choose the same methodology. Okay? So this is a typical way to analyze biomolecules. So today I introduce an example of project.
Sir, I have one question. That when you are deciding the excitation source for every biomolecules, you are taking absorbance band as a reference. So you are taking absorbance band as a reference, and then you are choosing the excitation source for each biomolecules. So as the excitation source is the absorbance peak, so there is no fluorescence background coming during the Raman?
It depends. So resonance effect enhances Raman signal, but it is accompanied by the real excitation of the chromophore, and it may result in the fluorescence emission. So in some cases, it happens.
Is it right to take the absorbance band, where the absorbance band is coming, to choose as an excitation source of Raman?
Right.
For dice molecule, is it right to choose the excitation source as where the absorbance band is coming?
You mean how to choose
The excitation source.
excitation source?
Can it be choose from the absorbance spectrum? Is it right to choose from the absorbance spectrum?
So by checking the absorption spectrum, you can find the one photon allowed transition, and that is available for the resonance Raman enhancement. So first we check the UV visible absorption and identify which chromophore gives which absorption peak. Then if some peak is matches with your interest, then we tune excitation wavelength to that position. So sometimes it's easy to choose the excitation wavelength if it's commercially available. Not easy, so but we can purchase. If not available, we need to convert the wavelength by some crystal or something.
Or in near as such that, as for example, a dye is absorbed at 520 nanometer. Is it good to take 532 nanometer as the excitation source?
532 nanometer excitation source, and so if there is a chromophore, or if the absorption is near 500 wave number, nanometer to put the crystal and change wavelength to approach. Sorry.
We doesn't have the opportunity to change the wavelength of the laser. We have some fixed laser. So is it good to take where the absorbance spectra is coming, choose the excitation source near the absorbance?
So you mean you have some certain one laser with certain wavelength, and there is your sample has different absorption.
Yeah. So it's good to take where the absorbance band is coming. Let's say dye absorb at 520 nanometer. Which wavelength laser we should try? 530 or 633?
So you mean you have a laser line 532 here. Then your sample has absorption here.
520.
520.
Yeah.
Then your question is what you can do?
And we have also 633 laser.
633.
Yeah. So which laser we should take to get the Raman spectra of that type, which is absorbance at 520 nanometer?
So probably this is more useful because the absorption band spreads.
Yeah.
So by approaching if the energy difference is closer, then
so if we excite at 532 nanometer, so there is a greater chance to get the fluorescence background because it is in the absorbance range of that molecule.
This is fluorescence peak. So
Absorbance peak.
So but when you excite this, then fluorescence occurs.
Yeah.
So the Raman scattering is a shift from excitation wavelengths. So if possible, you may choose this side. Then Raman band is here and fluorescence is here.
Yeah.
So you can separate Raman signal from fluorescence.
We do not have that.
So usually it's a program. If we can choose arbitrary wavelengths for sufficient intensity, or so that is the limitation of the experiment in every laboratory, I guess.
Yes. Thank you.
But 235 nanometer UV radiation is too strong for the biological sample. 235 nanometer laser.
Yes.
Is it not too strong for biological sample?
So, right, you're right. So, in my experience, I use 229 nanometer, and the sample concentration is 1 milligram per milliliter or so. Then I start measurement, resonance Raman measurement with 1 or 2 milliwatt, and after 5 minutes, intensity becomes 70%. So intensity becomes smaller and smaller time by time. That is, UV irradiation damages the sample, so the decomposition occurs. So every 5 minutes, I replace the sample to a new one, and accumulated 1 hour. So it's a problem indeed.
So
So if there is no question, let us thank him.